So hello dear students. So in this subsection I'm going to discuss interaction of nuclear radiation with matter, and in the first part I'm going to discuss the interaction of heavy charge particles with matter. That is, when a heavy charge particle which is energetic and which enters a certain medium, and how does it interact with that medium. Heavy charge particle means an alpha particle or a proton or some ion. So all of them are positively charged, and when they enter a medium, they interact with it in a certain way. So we are going to discuss that in this particular subsection. So what is meant by interaction of nuclear radiation with matter? So of course, nuclear radiation, as you know, it means energetic particles or some kind of energetic rays like electromagnetic rays which are emitted by unstable atomic nuclei whenever radioactivity is taking place. And these type of radiation, either alpha particle or beta particle or gamma rays, when they enter a certain medium like air or human tissue or some material in some detector, they lose energy while while moving through that medium. And this happens because of the interaction of the radiation with the atoms and the electrons of the medium. This interaction is the basis for both the biological effects of radiation and the functioning of nuclear radiation detectors. So basically, we are talking about interaction of radiation with matter, we are concerned with how it interacts with human tissue, for example, because it modifies the medium in which it is traveling. So if the medium is human tissue, it's going to change it and can damage it to a certain extent. Similarly, when we are talking about certain detectors which detect nuclear radiation, in that particular case, the type of interaction would depend upon the type of detector we are using and for the purpose that we are using the detector for. So any type of radiation, it interacts differently with matter because it has got unique properties. Each radiation has a certain mass, charge and energy. That is, each particle of that radiation has a unique mass, charge and energy. Because of these parameters, the interaction of those radiation with matter is going to be different for different particles. So like for example, alpha particles are heavy and positively charged, so they interact strongly with electrons in matter and lose energy rapidly. And only because their range is small, so they only travel few centimeters in air, or in case of a solid material like human tissue, they are only going to penetrate in the range of micrometers. Similarly, beta particles, which are much lighter, they are highly penetrating, and they penetrate much deeper than alpha particles. So they can travel up to few centimeters in a solid body, and not really few centimeters, but you can say uh, some millimeters, a few millimeters in solid body. And also in air they are highly penetrating and they travel large distances in air also, and they are significantly deflected by the collision with other electrons because they are light, so the deflection is large. Whereas in case of your alpha particles, the deflection is small because alpha particles are very heavy, and when they interact with the electrons of the medium, they are not deflected that much. And then in case of gamma rays, which are high energetic photons with no charge or mass, they interact very infrequently with matter, and they interact via photoelectric effect or Compton effect of pair production. depending upon the energy and the atomic number of the absorbing material. So basically, if the energy is large, then pair production can take place, and if the energy is small, then in that case photoelectric effect takes place. And so it depends upon the energy of the incoming radiation, and also it depends upon the type of the material. So different radiations require different types of detectors, and the reason being that no single detector is equally effective for all kinds of radiation. So any detector must match the type of radiation that is being uh, studied. So depending upon the type of radiation, the material is selected for the detector, and that material is going to be different for different types of radiation. So for example, alpha particles, which are not that penetrating, they have to be operated, the detector setup has to be operated in vacuum, because if it is not operating in vacuum, the air will absorb the alpha particles. So different kinds of detectors are used, like gas filled light detectors like ionization chambers or scintillators with very thin entrance windows are commonly used in this. And the window should be thin, because if the window is of these detectors is thick, then in that case again the glass window, whatever material is used for the window, is going to absorb the alpha particles. Then the beta radiation is more penetrating, but dense materials easily block those radiation. So Geiger-Müller tubes or plastic scintillators or semiconductor devices are well suited for beta rays due to their moderate penetration depth and relatively high ionization that they produce. So basically, of course, the ionization capability is much larger, because they transfer much larger energy to the other electron with which it is colliding. So gamma rays are deeply penetrating, so require very dense material to interact, because if you use a thin material, they will not interact at all and they will pass through that material. So high Z material like high atomic number material like sodium iodide are used, or scintillator detectors or semiconductor detectors like high purity germanium are used to ensure sufficient interaction with radiation. So let us discuss what are the different types of uh, interaction mechanisms which are possible when matter and heavy particles interact. So a heavy particle can interact by scattering via the nuclear scattering. That is, a heavy particle scatters via the nucleus of the medium, nucleus of the atomic species of the medium. So if it is elastic, there will be no energy loss, but there will be large angle deflection, and that is kind of a scattering which is known as Rutherford scattering. Then of course there can be inelastic nuclear scattering, in which it actually imparts some energy to the nucleus, and the nucleus converts itself into an excited state of that nuclear, and in that excited state it can either come back to the ground state by emitting gamma rays, or also it can transmutate. That means it can change its nuclear species, and some particles are lost in the emission in that process by the nucleus of the medium. And it is at high energies this kind of interaction is possible. Then of course you can have multiple Coulomb scattering one after another when small deflection takes place, because smaller energy is transferred to the nucleus of the medium. Then the most important one is it's the dominant loss mechanism, and that is scattering by the atomic electrons. Why is it dominant? Because the nucleus of the medium itself occupies a very small volume, and so the probability of interaction of the radiation with the nucleus is very small because of the small size of the nucleus. Whereas electrons occupy almost all of the space in the medium if it is solid. And so in that case, the probability of scattering with the electron is very large. So most of the time, the particles are being scattered by the electrons. And since the electrons are very light and the particles are heavy, so the transfer of energy is very small. And so to the actually as compared to the energy of the incoming radiation, so it only causes small deflection in the path of the radiation. And that kind of interaction is described by a very famous formula or equation called the Bethe-Bloch equation. Then of course you know that when a charge is passing through a medium, it gets deaccelerated. So basically due to that, it starts emitting radiation. So acceleration and deacceleration of a charged particle is going to result in the emission of radiation, and in that case that kind of radiation called the braking radiation or the Bremsstrahlung is possible. So in that case that kind of thing is also possible, and that would also lead to the decrease in the energy of the particle when it is traveling through the medium. So energy loss of heavy charged particles happen by Coulomb interaction with the matter most of the time, and most of the time it is with the electrons of the material, and this process called this process is called ionization energy loss, because in the process then atoms of the medium are ionized. So because the electrons gain energy and they either go to the excited state or they are released from the atoms, and in that case the medium becomes ionized. So this kind of ionizing radiation results in loss of energy of the incoming heavy charged particles, and that is the reason for the electronic stopping power. That is basically the power that is used that is required to stop the incoming ionization by the electrons. So this stopping power is defined as dE by dx. So here dE by dx is the change in energy per unit length of the inside the material. So inside the material, if the charged particles are traveling, so in 1 unit length that they travel, how much energy is lost? That ratio dE by dx is called the stopping power, or it is also called the mean energy loss per unit distance. So this is given by this particular formula where all these terms are described. So Z square is basically the charge of the incident particle, E is the charge of the electron, ME is the charge the mass of the electron, V is the velocity of the incoming rays, Z is the atomic mass, atomic number of the material or the atoms in the material or the medium, and A is the atomic mass of that material or the absorber, Na is the Avogadro number, rho is the density of the material, and so on, A as I have already defined, and this beta here is the ratio V by C, that is V is the energy, the velocity of the incoming particle, and C is the speed of light, and beta is the factor which is a ratio which is given by V by C. And gamma is of course 1 by square root of 1 minus beta square. So this is the formula given by Bethe and Bloch that tells you the stopping power of the material. So what kind of physical inferences you can draw from here? Of course, from the formula you can see that the stopping power varies at 1 by beta square. That is slower particles lose energy more rapidly as velocity increases, energy loss decreases and then increases logarithmically because there is a logarithmic factor also which is dependent upon the velocity. As you can see in the formula, if you step back into the video and look at the formula, there is an inverse dependence with velocity as well as logarithmic dependence with velocity. Then of course we have a Bragg peak, so energy loss at the end of the particle's path, that is at the time when the particle is about to stop altogether inside the medium, when its path ends, there at that particular juncture the energy loss increases tremendously, and this is called a sharp peak or sharp energy deposition, or it is also called the Bragg peak. And why is it so? Because when the particle slows down, at that point of time it starts capturing electrons. So the incoming radiation, when it slows down, it starts capturing electrons at the end of the path when its velocity is very small, its energy is very small. So from the surrounding medium it tries to neutralize itself and capture electrons. In that process it deposits a lot of energy in the material, and that is the reason for Bragg peak. Then you can see from the formula, if you step backward, the energy loss is proportional to z square. So it simply means that alpha particles whose z or the atomic number is 2 loses 4 times more energy than protons with the same velocity. That is, if the alpha particles are having the same velocity as the protons, they are going to uh, lose 4 times of energy more than the proton. Then the material dependence is also there. So it depends upon the z and the rho of the material. As we have seen, you can look at the formula and you can understand from there. Then you have the radiative losses are negligible. The Bremsstrahlung are negligible. Ionization is the dominant energy loss mechanism. As the particle slows down, leading to the rapid deposition at the end of the track called the Bragg peak, this is called as slowing down and deposition of energy, and results in a Bragg peak, so that at that particular junction the loss in the energy or the deposition in energy suddenly shoots up. So here in this particular you have a cloud chamber here. This circular figure represents a cloud chamber, and inside there is a source of radioactive material, which is emitting a lot of radiation, and you can see the cloud chamber is filled with some certain gas, and in that case these particles are moving. These tracks are showing the path of those particles, and you can see that after a certain point the path of the particle suddenly ends, and that path is not constant, it is variable. Some particles move a longer distance and some particles move a shorter distance. So that path which ends at a certain point, that point defines the range of the particle. So how much the particle has penetrated, it is defined by the range of the particle, range of that particular radiation. So if you plot the range energy relationship, that is with energy, if you are plotting the actual range or the path length of the heavy charge particles, then you can see here for air or H2 or aluminium or copper or lead, different materials, what is happening with energy, the range is increasing. As you can say on the y-axis, uh, it represents the alpha particle range or the proton range, and here it represents the deuteron range on the other axis in the y direction. And energy versus the range, it is plotted in the units of mg per centimeter square. And why is it plotted? Because in this particular units, why? Because dE by dx, which is the stopping power, uh, that would be not equal, its unit would not be mg per centimeter square, but you multiply it by density to normalize it. So then if you multiply dE by dx by density, then the units become mg per centimeter square, and then you normalize the data. That is, if the energy density is high, then of course, uh, if you're multiplying, the range becomes less because the density is high. So you multiply it by density so that different uh, materials lie on the same scale. So since you multiply it by density, then what happens is, uh, highly dense material whose range is small, its value after multiplication with density becomes large. So you can plot all the materials on the same scale. So this particular technique is used by multiplication of the actual range with the density to normalize the data, so you can visually see it for different materials. So here it is shown that the range increases with energy, as it is obvious. The energy, if energy is more, the range is more. So here we can look at a relationship called the Braggs-Kleeman relationship, also called the range mass relationship, not the range mass, which it will come later. First, we will discuss the Bragg-Kleeman relationship for heavy charge particles. So what is the Bragg-Kleeman relationship? It's an empirical relationship which is established by the experiments, and it relates the range of a heavy charge particle in a material to the range of another reference material, often air. So it is given by this particular formula. The range of a heavy charge particle in a material is equal to the range of the same particle with the same energy in air multiplied by rho naught, where rho naught is the density of air and rho is the density of uh, the medium, multiplied by A, which is the atomic mass or the mass number of the uh, material, and A naught is the mass number of reference material, that is air. So this shows that R depends upon A, and it is inversely dependent upon rho. So higher is the atomic mass of the medium, more is the range, and lower is the the density of the medium. Higher is the density of medium, lower is the range. Of course, A by A naught, this dependence is basically square root dependence. So our range depends upon the square root of the atomic mass of the medium. Similarly, we can have a range mass relationship of heavy charge particles. The range of a heavy charge particle such as alpha particle or proton in the matter depends on its kinetic energy and mass. So it is given by this formula. Range is proportional to the kinetic energy square divided by the mass. So for the same energy, if the charge particles or the radiations are heavier, then the range is smaller. Simply it is inversely dependent upon the mass of the heavier ion. So why is it so? Because the heavier ion has a greater interaction cross section with the atomic nucleus. So it represents or results in a more rapid energy loss. So the interaction of a heavier ion with the atoms of the medium, the interaction is more probable for heavier ions. So the cross section is higher, and so it deposits its energy more rapidly. So these kind of relationships are very crucial in understanding the interaction of heavy charge radiation with matter, because these kind of relationship gives a kind of a feel to it, that how the charge radiation is going to interact with matter, what would be the dependence of the interaction on the properties of the radiation. So these kind of relations are very important for in nuclear physics or radiation protection, for example, because we require different type of materials for radiation protection, and medical applications also, where we require how in the human tissue different radiations, how would the interaction of the radiation with the human tissue will depend upon the property of the radiation that we are talking about.